Okay, in this video we're going to take a somewhat different approach to the measurement of duration and convexity. We'll be focusing on something called effective duration and effective convexity, which are curve-based measures. Until now, we've obviously been computing both duration and convexity. Macaulay duration, then that critical measure, modified duration, and of course we've been computing annualized, or focusing on the application of annualized or annual convexity, but they were in fact yield duration and yield convexity measures, because yield was very much present in the computation of these things, even though we didn't really compute convexity other than by doing an approximation there using PV minus PV plus. But we did compute Macaulay duration, from which we derived modified duration, and yield was present in that computation all the time. We did discounting, we divided by 1 plus R, which was the yield to maturity to go from Macaulay to modified. Now the problem is, if you've got bonds with embedded options, so bonds with embedded options, that is call options or put options, which make those bonds callable or puttable, they do not have a well-defined yield to maturity. You can't compute realistically a yield to maturity for a callable bond, because you don't know when it will effectively mature. You can compute a yield to call, the first call date, the second call date, you can compute a yield to worst, but there is no such thing as a yield to maturity. So it's difficult to use yield-based duration and convexity measures, or pretty much impossible in these cases, unless you know the bond will not be called, because interest rates are so high that it doesn't really make sense to call the bond. So in such cases, if we've got bonds with embedded options, and this is likely to come up in a sort of theoretical question, you must use what we call effective duration. Effective duration is a curve instead of yield duration measure. Curve duration measure instead of your classic yield-based duration and convexity measures. So what does effective duration actually entail, or what does it involve? I highly doubt that you'll have to compute it. If you do, I'll show you the formula. It's like with approximate duration, to be honest. It measures the sensitivity of a bond's price to changes, but not in the yield to maturity, but changes in the benchmark, that is the government yield curve, to be honest. So e.g. the government par curve, which is the benchmark to which you add a yield spread. And something similar is done for effective convexity as well. Now, let's focus on two bonds or bond types with embedded options. First of all, a callable bond, because, as I said, you're likely to be tested on this in a theoretical way, and you need to appreciate how a bond, the yield price curve looks like, or what it looks like for a callable bond. So as usual, I'm drawing that classic setup where I've got the bond price over here and I've got the yield. But look, whereas before we had the yield to maturity, I'm going to now say benchmark yield, as in the yield on government par bonds. Classically, if a bond doesn't have a call option built into it, that's what you would draw. that convex curve. This is the shape of the curve for a non-callable bond. Now, the problem with callable bonds is that they can be called by the issuer, where the issuer basically can accelerate the repurchase, the redemption of the bonds, the maturity date, and pay investors back a fixed, predetermined price known as the call price, which is pretty much close to par value. So imagine that somewhere over here, I'm going to say call price. That's the price for which the issuer can call the bond effectively. And what will happen is, as yields go in this direction, normally the price of a callable bond, non-callable bond would shoot up. But that's not going to happen for a callable instrument because of the risk or the threat that it may be called. It's going to actually cap its growth at the call price. Nobody will pay for a callable bond a price that is higher than the amount for which it may be called and redeemed in just a moment by the issuer. So this green curve is the curve for the callable bond, and this distance over here, which changes depending on where we are. Okay, it wasn't supposed to get wider over here. That was just a drawing, inaccuracy. This is the value of the call option. The call option effectively caps the price appreciation potential of the callable bond. Now, a few important points. The price of a callable bond will always be lower than the price of a similar non-callable bond. Similar in terms of its parameters like coupon, time to maturity, etc. And issuer risk. Okay. The difference between the two prices is basically the value of the call option. Now, the call option is effectively held by the issuer, not the investor, because it's the issuer who can decide to exercise that call option at the detriment of the investor, of the bondholder. So it's something that lowers the price or value of a callable bond from the point of view of its holder. And please appreciate that the value of the call option is not constant. It absolutely increases in value as we go to the left in terms of the benchmark yield curve, yields. So call option has a higher value for sure for low rates, especially as compared to coupon rates. To the coupon rate on the bond, because recall that the whole purpose of calling the bond is to basically replace it with financing that is borrowed at a lower rate level. So if you've issued a bond, if you're the issuer, if you've issued a bond and you're paying a relatively high coupon and now interest rates have dropped in the market, allowing you to refinance at a lower rate, you'll call the existing bond and repurchase it using funding proceeds obtained from a fresh issue. So at low rates, call risk, or what we call call risk, goes up. That's the risk that the bond will be called by the issuer, and the proceeds that go to the investor will have to be reinvested in a lower rate environment at lower rates. Okay, and I just want to go back to my chart over here to show you something. Because we are talking effectively about curve-based risk measures like effective duration, and in a moment we'll also talk about effective convexity. please appreciate that we will be using or measuring what happens when there is a change to the benchmark yield, and I'm going to just like your curriculum does, symbolize this by delta curve as opposed to delta yield, which would indicate a change to the yield to maturity, which, as we said, for these types of bonds is not really well defined. Okay, let's now jump over to effective convexity as the second point. And look, as you can see, for a non-callable bond, effective convexity is basically always positive. Positive for a non-callable bond. The curve absolutely stays convex. The shape of the curve does not change. However, for the callable bond, which I've got down here in green, it is convex at higher rates, but then there is an inflection point and it changes to being actually what we in mathematics we would describe as concave. However, your text talks about this as being negative convexity. So basically the shape goes like this, and the inflection point I was referencing is somewhere here. It goes from having a slope that looks like this to having a slope that we draw on the other side of the curve. Now, that shift in convexity is quite important, and you need to kind of appreciate its existence. So, for callable bonds, it's positive convexity at higher yields, but negative convexity at lower yields. And please appreciate a point that I think I've already mentioned, but let me stress it again. The call price provides an effective limit a ceiling, a cap on price appreciation. So the call option, which is contained in a callable bond, limits the price appreciation potential of callable bonds. Effectively, nobody will pay for such a bond an amount that exceeds how much the issuer of the bond may call it for in a matter of maybe a year, 2 years, etc. Now, let's do something similar for the other type of option that may be built into a bond. That's a put option. So we are now switching our attention to puttable bonds. Puttable bonds. Okay. And same type of setup in terms of what we're going to draw. The chart with price on one axis, and we would normally have the yield to maturity. Now we're going to have the benchmark yield, so the yield on a benchmark bonds coming from the government. This is bond price, and once again, this would be the shape for a non-puttable bond. And we're going to draw the shape for the puttable bond, but just let's remind ourselves that with a put option built in, what the investor can do, not the issuer, the investor, is they can sell the bond back to the issuer for a predetermined put price, which is typically at par or close to par. Effectively, if this is the put price, because as an investor you can sell the bond over to the issuer for that fixed price or predetermined price, that will provide a limit to how low the bond can go in terms of its price depreciation. Now, The green curve, therefore, is our puttable bond, and this time we will draw the value of the put option as this distance. Please appreciate that the put option is held by the investors, so it's positive for them. Okay, and something absolutely important to appreciate, a puttable bond always has positive convexity. The shape doesn't change, it actually becomes more convex, it doesn't flip to the other side, so to speak. So, these are little points, theoretical points, that you need to absolutely appreciate for the exam to get ready for potential theoretical questions on this. Okay, the price of a puttable bond is going to be always higher than the price of an equivalent non-puttable bond. Okay, the put option is always favorable for the buyer or the holder of the bond, so for the investor. Put option value, and this time it's held by the investor, not the issuer. It actually goes up as interest rates go up. So as interest rates go, or benchmark yields go right over here, the value of the put option increases. What the put option allows me to do, if I'm the investor, is sell the bond for a price close to par value, get the proceeds out, and reinvest them into something with a better coupon. Whereas, obviously, if I didn't have the put option, I could sell the bond in the open market in an outright sale, but the price would be relatively low, probably, if interest rates have gone up in the meantime. Here, I can extract close to par value, the put price, and I can go and reinvest it at a better rate. So, as interest rates go up, the likelihood that the investor will sell the bond to the issuer goes up. Obviously, sell the bond to the issuer prematurely as part of exercising the put option, that goes up. And one little fine point to appreciate, a put option reduces bond duration, right? Especially at high yield levels, especially at high rate levels. What do we mean by that? Well, remember that duration can graphically be thought of as the slope of this curve. In the case of the green bond, that slope becomes flatter sooner than it is for the black bond or the black colored line here. It may not be that easy to see, but it really just flattens the bond potential for change, to change in terms of value when interest rates are changing. Okay, right. Now on to some measurement topics. I don't expect you to have to measure this. The learning outcome statements in your book state things like explain, so describe, but just in case. Oh, and one more thing, before we get to the measurement, effective duration and effective convexity. So two of these curve-based measures are also going to be relevant in the case of mortgage-backed securities, which are discussed in later videos on this fixed income playlist. The reason why they are relevant is that under mortgage-backed securities, or with mortgage-backed securities, investors buy a security, an instrument, whose cash flows are a function of how people or institutions are paying, repaying their mortgage loans, be they residential or commercial. And there is typically an option to prepay your loan early, repay it early, and by refinancing it at lower rates. So with MBSs, you can think of them as containing an implicit call option. The borrower can repay their loan early and refinance at lower rates. That's why these measures are relevant to these securities as well. Now, for the actual calculation, which I don't expect you to have to do, but if you do, it's relatively easy. Effective duration is computed by taking PV minus, so the value of the bond if there's been a drop in the benchmark yield, minus PV plus, the value of the bond if there's been an increase in benchmark yield, divided by 2 times the change in the benchmark yield, and I previously described this as being delta curve, multiplied by PV0. You should hopefully appreciate that this is the same, or essentially the same formula as we had for modified duration, and we applied that formula before in previous videos. We computed stuff based on it, except that over there we used, instead of the delta curve, we used delta yield, the change in the yield to maturity. Here you just use change in the benchmark yield curve. So this stands for a parallel shift in the benchmark yield curve. How much have government yields effectively changed? But the problem is, just like with other duration measures we've encountered so far, we are assuming that all the benchmark yields change in parallel, so the shape of the yield curve stays constant. Something will be changing, for an assumption that we'll be going away from in the next video when we do Q rate durations. Now, these PV minus and PV pluses, you will be given these in the case of bonds containing embedded options, because you can't just compute the new price of a bond given a yield change. If it's got a call option or a put option based embedded into it, you must effectively calculate these using option pricing models. And when you get to level 2 of the CFA exam, you will be doing some basic calculation of this using the binomial approach. And nobody will ask you to do this in the exam. You may be given the new price following a benchmark yield drop or a benchmark yield increase, and just need to plug it into the formula, just like we did with approximate modified duration. Now, that was effective duration, and there's a similar formula, and it's actually a copy, almost a mirror image of the formula we had for approximate convexity. So effective convexity is PV minus, this time plus PV plus, and minus 2 times PV0, the sort of the outset price. And we've got that same change in the benchmark yield curve over here. It's expressed, sorry, let me use the same color to draw this arrow. We square this and multiply it by PV0, and if you go back to your notes or the video for approximate convexity, you'll see that it was the same thing. Now, these two measures may also be computed for option-free bonds, and you'll get a similar result to what you'd get with modified duration, with some little differences for reasons that are quite theoretical. I don't think we need to necessarily go into that. Now, once we've got these things computed, we can apply them just like we apply annualized modified duration or approximate modified duration. How do we apply them? Well, to compute the percentage change in the full price of a bond, as you may remember, and this is approximated by the minus of effective duration, previously we had modified duration, times the expected change in yield, here it's going to be the benchmark yield, plus, and you should remember this from our previous videos, half of the effective convexity multiplied by the change. Previously we had yield, now we're going to have delta curve squared, close bracket. And if you are given effective duration and effective convexity, please just treat them the same as you would have, you would treat normal duration and normal convexity, sort of the previous ones. Plug them into the same formula and use, don't be surprised to see that you're given a change in the benchmark yield instead of the yield to maturity. In any case, the learning outcome statement for this section states explain. So I don't think you'll have to do these computations, to be quite honest.